Hello everyone, welcome to the presentation of my thesis defense, which is called Post-Migration Seismic Data Conditioning on a Merged Dataset. The committee members of my thesis are Dr. Heather Beadle, who is the chair, Dr. Brett Carpenter, and Dr. Matt Pranter. This is the outline that I will be covering today. I'm going to start with the motivation and introduction and talking about why do we care about seismic merged datasets and why it's important for seismic interpreters to learn to handle post-migration seismic data conditioning methods. I will explain the theory behind spectral balancing and structure-oriented filtering and the combination of these two techniques. Then I'm going to discuss with you the results and compare what I obtained with what we were expecting from the application of these methods. I'm going to finish with a conclusion and acknowledgments. So to start talking about merging seismic datasets, we know that in the past 40 years in major basins like the Gulf of Mexico basin, there have been a lot of acquisition of seismic volumes that were reprocessed and merged during the time. And the merging of seismic datasets is very common today for several reasons. One of those reasons is that it becomes the work of the seismic interpreter more simple, since instead of looking at several volumes at the same time, we are just looking at one single volume. And another advantage is that it gives a broader coverage of the area that we are studying, and that of course bring economic benefits. The volume which I am using for this project is located in the offshore Texas in the Gulf of Mexico in the Matagorda area. And as we can see here in this cartoon, it is compounded by two legacy surveys, which is the Matagorda teleline that it's in purple and the Matagorda Island in pink. So as we can see in the table below, these different volumes were acquired at different times and using different acquisition parameters. And also we can observe that they have different orientations, the survey grids of each volume. So these are all the details that the processor needs to take care about when they do the merging process to create the master grid to merge the volumes. So the black polygon is representing the portion of the volume that I am using in this study, in which it is visible a contrast of amplitudes and frequencies at the seam of the two legacy surveys. So this vertical line is showing this union between the two legacy surveys, and we can see here in this cross line that we have brighter amplitudes in the northeast and dimmer amplitudes at the southwest. This is also visible here in this envelope map, and we can see how we have a sharp contrast here that doesn't have any geological meaning. It is a product of a merging issue. And also we can see several faults in the cross line and in this coherence subtle filter map. So as the seismic interpreters, we always want to have a good quality and high detail seismic datasets to do better seismic interpretations. So that's why it is important for us to know how to handle these seismic post-migration conditioning methods. So first, because they quickly improve the data quality, it reduces the cost of reprocessing, because if we know how to improve our data sets, then there's no necessity to come back and do a reprocess of the volumes. And last but not least, sometimes we don't have access to the raw data for reprocessing. So it is important to know what tools we can use to do the best thing with our data sets. So today I am gonna show you how I explored spectral balancing as a technique to reduce the frequency and amplitude mismatch in the seam. and also to improve the frequency content of the dataset. Also, the use of structure-oriented filtering to reduce the noise and enhance the stratigraphic discontinuities, and the combination of these two techniques to enhance the quality of the seismic volume. So I'm going to describe the geological setting. Even though I'm going to discuss a geophysical process in this presentation, geophysicists should always use their understanding of geology and have geological criteria to make better decisions when we are improving the datasets. So I will quickly review the geology of the area. This region is characterized by significant faulting events and fluctuations in sedimentation patterns. The sediments are mainly constituted by sand shale interlayers that have been affected by lithic faults that detach from a shale base. We can see in this cartoon the interpretation of two horizons that belong to the Miocene, and these allow us to see what are the dimensions of these faulting systems, as we can see how the thickness increased going basinwards. This is also indicating that the faults were active at the time of deposition, and the Miocene sediments are severely affected by these faulting events. I try to replicate this seismic section with the Matagorda Island dataset. And as we can see again, we can see a lot of faults everywhere that are affecting the data. And if we do an interpretation of a key horizon, like the blue one that is here, and run coherence, we can obtain a map like the one that we can see here, where the faults are visible and we can see how they are impacting greatly the data. So it is important to know that we have this significant fault activity here, because in enhancing our data set, then we need to understand how faults behave. So they help us to understand too how these seismic data conditioning methods are helping to enhance their visualization. So to start assessing the data, I started by doing the basics. So I observed the data through time slices in the amplitude and different attribute volumes. And then I mapped major horizons and computed different attribute volumes. In this slide, there are 4 horizon slices that correspond to the 4 horizons in the seismic section. We can see that there is a sharp amplitude contrast in all of the maps. It is more visible, especially in the shallower maps, which are the cyan and the yellow that we can see here in the section. But we still have this contrast when we go deeper. So this is also showing that it is important to understand to detail why are we having amplitude contrast, even when we are doing a regional exploration. So given this observation in the amplitude and frequency contrast, and given the importance of fault behavior in the area of study, then improving the quality of the merge becomes crucial to do more accurate seismic interpretation. In this slide at the left, we have a simplified workflow with the methods I used in this project. And as I mentioned in the previous slide, I started by basically observing the data and looking at attributes, and then I performed a frequency analysis of the data sets followed with the different application of conditioning methods. I evaluated each method independently to see how each step impacted the data and then their combination. So when we do the frequency spectrum analysis, here we can see at the right in light blue the frequency spectrum of the original dataset. Then in red, the structure-oriented filter dataset spectra, which is basically the same. We have very few differences between the two of them. Then in orange, the spectral balance dataset, and in green, the spectral balance SOF dataset, the combination of both. This plot is showing us that structure-oriented filtering is not changing the frequencies of the data. So this process doesn't affect the frequencies. So if we come back and we observe only the original dataset spectra, we can see that the frequency content of the merge is very poor. It displays a dominant frequency of 25 Hz and a remarkable decay of frequencies after 40 Hz. So the first technique I applied to the volume is spectral balancing. The application of this technique aims to enhance the existing frequencies by flattening the frequency spectra in the usable ranges of frequencies. So it is important to distinguish this methodology from frequency broadband because this method doesn't simply add high frequencies to the data, but it works on the existing frequencies and it relocates the usable frequencies of the dataset to their ideal level. So we can see this in the plot. Ideally, a seismic interpreter could apply a constant filter along the entire survey, so that would create a greater frequency content in the volume and would preserve relative amplitudes. But in this case, since I have a mismatch of frequencies and amplitudes at the seam, I decided that I wanted to treat my data in a more aggressive way, and I did a not that amplitude-friendly method, and I applied the trace-by-trace spectral balance. So this technique needs to be used carefully because it can, as I mentioned, it can harm relative amplitudes in a way that we can miss some information that is important. So it is recommended to use this technique always with well control. Then again, the SOF and spectral balance and SOF datasets show that the structure-oriented filtering technique doesn't change the frequency of the volumes. So we already saw what is the spectral balancing. Now let's move forward and see what is structure-oriented filtering. This technique is commonly used in the industry to enhance faults and stratigraphic edges visualization. SOF smooths the data while it preserves the energy in the parallel direction to the structural dip. This means that when the filter finds a fault or a stratigraphic discontinuity, it will preserve it. It's not going to smooth it. So we can observe how this filter works with an example of the dataset. So I took a section where we have some faults, and we can see how after applying structure-oriented filtering, we have a sharpened definition of the fault planes. And also we can see how it has smoothed the data. So this is how the filter works. And also, while doing this, it also suppresses random noise and cross-cutting coherent noise. And this is how this residual noise looks like. So now that we have the basic understanding of the methodologies applied in this project to improve the quality of the data, let's look at the results. In this slide, we are observing at the seismic crossline. We can see the orientation of the line in the small reference map at the left, which is the blue line. And these four seismic sections are the original, spectral balance only, structure-oriented filter only, and the combination of the two techniques. And we can observe that how at each step the data is modified by each technique. So in the spectral balance datasets, we can easily see that we have more frequency content. We can tell this by seeing that the reflectors became thinner, and we have much more detail of what's happening in the seismic. Then in the structure-oriented filter dataset, it seems like it looked very similar to the original dataset, but it is showing in much more detail the faults as we would see it in the original dataset. And then in the spectral balance and structure-oriented filter dataset, we actually have the combination of these two methods. So the idea of applying spectral balancing and then structure-oriented filtering is reveal new features with the spectral balancing, reveal features that we are not able to see in the original data, and then with the structure-oriented filter, enhance the visualization of these new features revealed in the previous step. So let's look at this in detail. We can see here that we have the two faults that in the original dataset look like they are. Maybe a single fault plane that is segmented, but then when we look in detail in the conditioned data, we can see that actually there is more than one fault plane. So this is actually really cool, and it's showing how spectral balancing is giving much more detail, and we can have a better understanding of what's happening in the subsurface after applying this method. We have much more resolution. Now let's move to see what happened at the merge, because don't forget that we are dealing with a merged dataset with a mismatch of amplitudes at the seam. So again, we have the seam, and we can see how we have different, the amplitude looks brighter at one side compared to the other. And we can see that spectral balancing is not solving the problem completely. It's much more better, but we still have the seam. So let's see what else we can do with that. This amplitude contrast can also be seen on attributes. Here we are looking at envelope and peak magnitude before and after seismic data conditioning. And so we have the red line indicating the merge, and in black arrows, I am displaying some faults. Amplitude attributes are not the best attributes to see faults, but still we can see and anticipate that something is happening with the faults, especially in this area. And then we have, again, the sharp contrast of amplitudes, that we can see that it has been reduced after spectral balance, but we still have it. The reduction of the difference in values has been from 20 to 30%. So let's see if there is something else that we can do with it. So to address this problem, we still have one more tool. We can use automatic gain control, AGC. This technique is well known at the processing stage because it attempts to recover the amplitude of the signal that has been lost during the propagation of the wave different mediums. So let's see how it works. Here we have before AGC and after AGC, and I am using here a long window. Basically, the length of the window in AGC is going to determine how aggressive are you going to be with your data. A long window means less aggressive, a short window means more aggressive. So here I'm using a long window, and as we can see, when we go deep, we can recover some of this amplitude signal here, and that's what we are looking for. That's exactly what the method does. And again, since I'm using a long window, I am still preserving some relative amplitudes as the one that we can see here, which is very good. We don't want to harm the amplitudes that much. But still, we are changing the nature of the reflection of our seismic reflectors. So it's a tool that needs to be used with careful. Let's see how AGC works at the seam. So again, we are looking at the original data set, the spectral balance data set, and spectral balance with AGC using a long window. This is 0.5 seconds. This is a long window, and this is a short window, 0.05 seconds. So if we look at the merge, we can see that, yeah, AGC using a short window does great to get rid of the problem of the merging. But we should also consider another changes happening in the seismic. So if we do some interpretation on this cross line, we have the key horizon, the blue horizon, that is key because it is consistently bright along the across the survey. It is continuous and it is easy to follow, and we can distinguish easily what is below and above this reflector, so that makes it key. And we can see that it is still a followable horizon here, and applying AGC with a long window, well, it is changing it, but still we can follow this horizon. But then with a short window, this horizon becomes exactly the same that any other horizon in the seismic. So we have to be careful with that. Another thing that we have to consider is that if we are doing amplitude analysis on our seismic, then a short window is going to harm the data that much that we are going to lose bright spots like the one that we can see here. Here in the original dataset, we can see how these reflectors becomes brighter here close to the fault, but after the application of AGC using a short window, that bright spot is not there anymore. So this tool is recommended to use if we have well control, if we can track how the amplitudes change before and after the application of AGC, and also it can have another applications such as stratigraphic or structural interpretation, but not for seismic amplitude analysis. So far, then let's keep moving. We have seen how post-migration seismic data conditioning methods have impacted the amplitudes in the merged volume, but let's see the frequencies. Here we can observe the before and after seismic data conditioning of instantaneous frequency and spectral mean frequency. So by looking at these maps, we can observe that before, in the original data sets, we have a very limited frequency content. We can tell this by looking at the color bar, if we use it as a reference of the values of frequencies, that we have yellow and green colors. So we are going to move from 30 to 40-ish hertz. Same here, maybe lower values. After seismic data conditioning methods, if we use again the color bar as a reference, we can see that we have a greater range of colors indicating that we have more frequencies in the data. So red line indicating the seam of the seam of the two legacy surveys, and how before applying data conditioning methods, we have a sharp contrast of amplitudes that doesn't have any geological meaning. We know that is happening because it's an emerging issue. But after spectral balancing, we can see that we don't have that sharp contrast anymore, which is really good. This is something that we were looking for when we started this project. This is one of the problems that we were addressing, and we were using conditioning methods to try to get over it. And we can see that spectral balancing is helping us to overcome this problem. Doing some more analysis on this map, again, the black arrows are showing faults, but we know that frequency attributes are not the best to display faults. But again, same as amplitudes, we can see and we can anticipate that something, we can see some other details here close to the Clemente Thomas fault, which is this one here. So let's look at an appropriate attributes to see faults. Here we are looking at Sobel filter, which is a similarity attribute. The black lines are representing faults. Whatever is not black is no fault, basically. So again, we have the original spectral balance, structure-oriented filter, and the combination of the two techniques. And if we see here in the footwall block of the fault, apparently in the original data set, we can see that there is no deformation, there is no faulting in this block. Same in the structure-oriented filter dataset. We don't see any evident faulting events. However, after the application of spectral balancing, we can see that there are some features showing up that weren't visible before. So spectral balancing is showing us some more detail, and we can see that these small scale features in the seismic section are displaying a very small scale deformation of the horizon. So this is important because we can see that spectral balancing is helping us to resolve features that we weren't able to resolve before. And this is a big deal if we are doing some reservoir characterization where we need a level of detail that requires to define these small features. So here we have how they look in all of the seismic sections. And now let's look at another example, also looking at faults, and we are now analyzing the hanging wall block. So again, the thick black line is representing the Clemente Thomas fault, and we can see some small faults showing up here that we can see in the seismic dataset. In the original dataset, they are visible, and same in the other volumes. And now, if we look at the space that we have between the fault and these little faults that we have just seen, there is apparently nothing happening there. And after spectral balancing, this map looks like is showing noise or something like that. So when we analyze this in detail, we can observe that that noise is not actual noise, but it is displaying some of, again, small scale rugosities of the horizon, a very small scale deformation. So again, this is a great deal if we are doing reservoir characterization, if we are looking at the detail on the seismic. This is very important because it allows us to see if we are characterizing a seal or a reservoir, if we have potential fractures happening here or not. So spectral balancing is helping us to resolve this small scale deformation. So we have seen how this seismic data conditioning workflow works in amplitudes, in frequencies, and in geometric attributes. So let's now take a final look at the workflow, and we are going to analyze this special time slice. Here I am co-rendering peak magnitude, peak frequency, and subtle filter similarity at 932 milliseconds. And well, we can see that there is, again, a sharp contrast of frequencies at the seam that we can see how the colors change from one side to the other. And after the application of spectral balancing, we don't have that contrast anymore, giving more consistency to the interpretation. And we still can see faults in each step. However, when we look in detail, we can see that the faults after spectral balancing are somehow hidden with some noise. So we can see that spectral balancing is exacerbating the high frequency noise already existing in the dataset, which is an undesired result. We don't want to have noise contaminating our data and our interpretations. We want to have a clear understanding of what is happening. We can see that SOF cleans a little bit that noise that was produced before. So that's good, but anyway, we still have a noisy image. And finally, if we look at the stratigraphic edges, we can see a surprisingly result. So here the red arrow is indicating the edge of a stratigraphic channel, probably the edge of a river that is visible in the original dataset. And then we can see that SOF is enhancing the visualization of this feature. Same with this little one here. But after the application of spectral balancing, we see that that feature disappeared. And this is a surprising result because, as I said at the beginning, as I've been saying in this talk, we are applying spectral balancing to have more detail of the stratigraphic and fault features in the volume. And seeing that one of the features disappear is something really unexpected. So let's look in detail what is happening here. Again, we have a zoom area of this stratigraphic feature, and we can see in the original dataset how we can see it, and we can correlate the edges visible in the map with the seismic, and how they can also be seen in the structure-oriented filter datasets. But then in the spectrally balanced datasets, they are not there anymore. So as we apply the spectral balancing to enhance the frequencies, and we played with frequencies, then the answer to what is happening here should be in the frequencies. So let's take a look to the frequencies. Here I am displaying again the same figures before and after conditioning methods, and I'm also displaying multispectral coherence. Here we can see coherence, but only in the three frequencies that I choose here, that are 20, 30, and 40 Hertz. So if we do some interpretation in this portion of area and we delineate the features that then disappear after conditioning methods, and if we put this interpretation in the multispectral coherence, we can see that these features are in the cyan color. So that means that this feature is tuned at 20 Hertz. Then we have one more feature happening here that it's also visible after this one is visible after the application of conditioning methods. And again, if we see it in the multispectral coherence, we can see that it is a mix of frequencies. We can see different colors. We can see yellow, cyan, pink, or magenta. And so it's a combination of different frequencies, and we were able to tune it after spectral balancing. So here at the bottom of the slide, we have two cartoons that resemble the frequency spectra that we analyzed at the beginning of the presentation, and of the original and spectral balance dataset. So as we could see, we are tuning these frequencies in the original dataset at 20 Hertz. And we can see that the original dataset does a great job tuning features at 20 Hertz, right? But after the application of spectral balancing, we are losing some of the energy associated to the features tuned at 20 Hertz. So this is what explains why we are not able to see these features, especially after spectral balancing, which is something curious and cool and unexpected. Then for the other feature that is tuned at, let's say, 40 Hertz, we are able to see it better because we gained some energy to see this feature. So this is a pitfall in the application of spectral balancing. Is something that the interpreter now should take into consideration when it's applying spectral balancing. And now we know that we should be care about the tuning frequencies after the application of spectral balancing. We should check how they look after its application. So, as a conclusion, I have applied a post-migration seismic data conditioning workflow consisting of spectral balancing followed by structure-oriented filtering to enhance the quality of the merged dataset with a mismatch of frequencies at the seam of the two legacy surveys. The application of spectral balancing improved the frequency distribution across the seam and generated a more consistent geologic interpretation and allow us to reveal small-scale features of great relevance for reservoir characterization. We used an additional tool, AGC, to overcome the mismatch of amplitudes at the seam, but we must be cautious about the application of this tool since it can severely harm the data. And finally, we found a surprisingly result in the application of spectral balancing, and it showed a pitfall at tuning frequencies. So these are the acknowledgments of this project, and these are the references. Thank you.